The screen is visible to all. Okay. Last class we discussed about the pressure distribution with respect to Pascal's law, hydrostatic law, and also we discussed about the pressure measurement with respect to atmosphere and gauge pressures. And later we solved some of the problems on piezometer. Today we'll take up some more problems on piezometer or manometers with the different types. So coming to the manometers, we have simple U-tube manometer, inverted manometer, that is for the self-study. That also will discuss one problem. Then we have compound manometer and other types. So we'll take up in the examples or the numericals. We'll see what are the types of manometers, how to write the equation or how to solve those problems to find out the unknown pressure or the unknown head. So coming to those problems, I think we have stopped at this point. Yes, this problem, right? Manometer which is having a U shape like this. Two U-tubes are there, which is connected to one of the pipe, and other side it is kept open to atmosphere. Yes. So last class we discussed about the details of this manometer. Now we'll see how to write the equation for this manometer. So coming to this part, as I told you, at the U-shape side, if you see, as in the sketch, we have taken the half of the part, that is red color line. If you see where the dimensions are given, at that point we have separated that U-tube and we are trying to write the equation. So one side there is atmospheric pressure, other sides there is a oil head. Okay, and section 1 if you see, or the datum line 1 if you see, either top side or bottom side, those two heads and the pressures are going to be neglected, because both side the head is same, both side the liquids are same. Okay, one side it is mercury liquid, other side if you take the datum line 1-1, there oil is filled. So both side the head and pressure are same. We are not considering the U part of the manometer, because both the heads are going to cancel each other on left and right side. So apart from that, we left with the head with respect to 800 mm of oil, and we left with mercury head 350 mm. So these are the only two heads which are acting in the manometer. So on which side we'll consider the different heads, we'll see in the equation writing. And oil specific gravity is given, that is 0.9. You can find out with respect to water, or the relation of specific gravity, you can find out the density of the oil, that is 0.9 into density of water. You can find out 900 as the density of the oil. And mercury also we should know the standard values, that is density is around 13,600. So using these known and unknown numbers, and we need to find out, see here in the figure, an open manometer is connected to a pipe to measure pressure at A. Pressure at A we need to measure of the pipe. This pipe is a long pipe. One small hole is made to connect this U-tube, small U-tube with a small diameter. Okay. So now we'll go to the equation. See here. Now either you can take the half on left side or on the right side of U-tube, or on the pipe side also. So depending upon that, here what they have done, they have taken atmospheric pressure and other heads on one side. So with respect to pipe, if you see here, with respect to pipe, the atmospheric pressure and the mercury head and the oil head, these all can be added, because see with respect to pipe, oil is trying to push the column of this mercury, and mercury is overcoming the atmospheric pressure and it is rising up. Okay, so one side, if I consider only pressure A one side and other tube on the right side of the equation, so what we can do here, as this pipe is rising upside and liquid mercury level is also rising upside, so I can add both the things, that is P atmospheric plus head due to, or the pressure due to mercury, rho gh of mercury and rho gh of oil, and from this one can find out the pressure of the pipe. So find out this pressure of the pipe, and also we are adding the atmospheric pressure here. So whenever, if you neglect atmospheric pressure, that will become the gauge pressure, or if you consider the atmospheric pressure, or if you add the atmospheric pressure, that will become absolute pressure, because absolute or the total pressure is nothing but atmospheric pressure plus or minus gauge pressure. So all of you check this value, whether it is 1,55,154.8 Newton per meter square, or you can write it as 155.15 kilonewton per meter square. So this pressure is with respect to atmosphere, or the zero gauge pressure. So zero pressure or the vacuum pressure, if you consider, then we can call it as absolute pressure. With respect to atmosphere, if you want to tell, then we need to subtract that atmospheric pressure. So check this substitution and check the answer. So now onwards, the properties of water, the properties of mercury, and the atmospheric pressures, all these things we should know as a standard. Even though if in the problems, if they are not given, we need to take or assume these numbers for solving the examples. Only for other fluids like oil, some other fluids like glycerin and something, or kerosene, they may give specific gravity, and from that we need to find out other properties. His answer is coming correctly. Okay. So next part, we discuss this in the pressure measurement. So whenever we want to find out device pressure or the gauge pressure, so we are taking absolute pressure minus atmospheric pressure. So for example, if we go back and see the pressure measurement here, so one can understand what is the importance of that equation for finding gauge and absolute pressure separately. So here you can observe. So whatever the pipe pressure we have found out with respect to atmosphere, or by adding the atmosphere pressure, so that will become total pressure or the absolute pressure itself. So wherever you are seeing absolute pressures, it is with respect to measured from absolute zero pressure, and it is considered with atmospheric pressure, either negative or positive. On the right side of the sketch, you can see negative or positive. It is by subtracting or adding the atmospheric pressure only. If it is more, it is more than atmosphere. So in such cases, if you want to find out only gauge pressure, then we need to subtract the atmospheric pressure. Then it will become gauge pressure. Means from the atmospheric pressure considering at 0, what is the pressure acting. So with respect to atmospheric pressure, if you tell the any value, that becomes atmospheric pressure or the gauge pressure. If any value, if you tell with respect to absolute 0 pressure, that becomes the total absolute pressure. So same principle is used here to find out the gauge pressure. So they are going to subtract the atmospheric pressure here. Here, gauge pressure is equal to absolute pressure minus atmospheric pressure, or you can write P total minus P atmospheric. So that will give us what is the gauge pressure with respect to atmosphere as the reference. So if this is understood, we take some other types of problems. Okay, we'll take differential manometers, one of the type. Okay, we'll take this type. As this you can note down. Evaluate the differential pressure. So whenever two pipes are connected with U-tube, that is called as differential manometer. Because in this type of manometers, the difference of pressure at pipe A and pipe B, due to those difference of the pressure, the manometer is showing some reading. And sometimes the question may also come, when there is a flow in pipes, it may not be constant. Yes or no? The discharge or the flow rate or the velocity or the pressure in the pipe, it may not be constant throughout the length or the for a given time. So what we are assuming here is, for a given point of time or for a given instant, both the pressures A and B are going to remain constant with respect to those references, and due to which in the manometer we are going to observe the head difference, and it will remain for a given time constant. And for that given time, or say for example the valve is kept open for a given opening, and the pump pressure or the flow pressure is maintained constant in pipe A and pipe B separately. But for a given time, the manometer reading may remain constant. So we are assuming these readings, whatever is given in the problems, will remain for some time. Then we can take those readings and find out what is the pressure at pipe A and pipe B. So coming to this example, here what they have done, evaluate the differential pressure between two pipes. So we need to find out the difference in pressure PA minus PB. Okay, difference in the pressure they are asking. And you can see pipe A is containing the liquid with specific gravity 0.92. Okay, and pipe B is containing liquid of same specific gravity 0.92. So both the pipes are having same fluid, and in the manometer which liquid is given, we'll see that. So most of the time it will be mercury. If it is not mentioned, it should be mentioned in the question. So here both sides is not mentioned. So we'll check what they have used. So same fluid you have to use, like mercury and other fluids. Then here in the heads, if you see, I will take the lowest part of the reading of the manometer. So lowest part is the below this 20. That line, if you see, this is the lowest line of the mercury head. Okay, so from this we do all the measurements. Now as per the sketch they have given, the lowest head of the mercury to the highest head, means the head difference between the mercury levels or the liquid levels in the U-tube, they have given 20 centimeter, and the difference in pressures or the difference in head, sorry, not pressure difference we need to find out, PA minus PB. The head difference, what they have given, H difference is from the pipe A and pipe B is 50 centimeter. Both the pipes are not at the same level, they are at a different level. And as we discussed in the hydrostatic law, whenever there is a level difference in the pipes also, there is some head developed by one of the liquid. So as per this example, the liquid A is developing some head because of 50 centimeter difference. And the difference between this 50 and 20 they have given, that is nothing but the center of the pipe B or the head of liquid B, whatever is there with specific gravity 0.9, is making head of X. That is not given. So by using this unknown value X and other values, we can find out the pressure difference, because they are not asking PA and PB separately. If in this case, giving X as unknown, if they would have asked PA what is the exact value or PB what is the exact value, it is not possible. Because in the equation, we should have only one of the unknown. Then only we can find out the value. Otherwise, we can approximate and find out. So in such problems, what they told, you find the PA minus PB difference only, not the values. That should be in the mind. Then what we need to find out, if X is known, one can find out what is PA minus PB. Okay. So now coming to the writing the equations. So again, I recall all the procedure to write the equation. So from the pipe, whatever the pressure is coming on one side, we can take it as positive. And whatever the liquid levels are coming downside, we can consider it as positive. And the liquid levels which are rising upside on the other side, we can write it on the other side of equation, or you can subtract it. Okay, with the same pipe. And the liquid head which is there for the B pipe, which is also with respect to A, it is rising, or it is at the above point. So that also you can consider on the right side positive sign, or left side if you take, you can take it as negative sign. Because pressure A and pressure B both are acting opposite. Are you understanding? So either you can write PA minus PB, then heads of all the liquids with respect to pressure equations on all the one side, positive, negative, all the one side, and you can make it equal. But easy way is, as per my suggestion, you can go by dividing this U-tube into two halves. So what I'll do here, only one U-tube is present. I will make it exactly half at these lines, 50, 20, X, whatever the line is given. At that line, I will divide this manometer. Now I will take left side of the differential manometer, right side of the differential manometer. So in between, I'll put one equal sign. So that what I'll write now, PA plus, see here, PA plus downward acting pressure. Earlier case, we have taken upward acting, like an inverted manometer, but here it is downside. So downside pressure means the fluid is pressurizing the mercury level to move up in the other side, so that the liquid head on the left side and pressure on the left side, will take it as positive. Now we need to find out the pressure on the liquid or by the liquid, that is rho GH. Rho is 0.92 into 1000, 920. 9.81 is the gravitational force G. H is 50 plus 20 plus X. So X is not given. We'll see it. So total head of liquid, or the pressure due to this head of liquid, what is applied on the mercury on left side, is 70 plus X. So this is given in centimeters. They have converted into meters. So that is 0.7 plus X on the left side. On the right side, if you see, pressure B is acting on the pipe B because of pipe B, and this pressure is trying to oppose the mercury head, and both are on the right side as we have taken. And with respect to left side pressures, if you see, these pressures are negative sign because those are rising upwards. Mercury head is rising upwards, liquid is also rising upwards of pipe B. Okay, keeping that in mind, equal to right side whatever the terms are there. Now PB plus the head. What is the head? Again rho GH. So rho GH for mercury, if you see, I take 13,600 G into H. H is 0.2 meters of the mercury. And for this liquid, if you see, liquid B, if you see here on the right side, small level of the liquid is present with X head. That if I consider, again same liquid is given of same specific gravity 0.92. I will take 0.92 into 1000. That will be 920 into 9.81 into head of the liquid. So head of the liquid is again unknown here, X. So I'll write that X. So this becomes the writing equation for the differential manometer, balancing both the sides. All of you understood how to write the equation for a differential manometer? Okay. Okay, we'll move further. So once we substitute all these values, so you can find out PA minus PB values. And as per these terms, I think they have cancelled X also, because X is not given in the problem itself. And because of unknown value of PA and PB, we cannot find X only. So because of this 920, 9.81 common terms, they might have cancelled X. So you just check whether the X can be cancelled or not and find out PA minus PB what is the value. Because this term will become X, term will become X minus X if you take it on left side or on the right side. Both X terms, if you take one side, it will become X minus X of given quantity. But PA minus PB if you take, you cannot cancel, because pressure of P and PA plus PB both are different, as given in this problem you can see. As per the sketch, we can understand PA is more, PB is less. Now see here, in the sketch and question they have not given mercury, but for problem they have taken mercury. But actually it should be mentioned. There is a mistake. So find out the pressure difference between two pipes. Here it is coming around 20.3 kilopascal. Others, are you calculating? Okay. 20365.561. One more answer is 0.64. Okay. 0.56, 0.64. Okay, whatever value you get, you just write it. 20365. 365. Okay. So after decimal point, there is some value difference, not an issue. Before decimal, if any issue is there, we'll correct in the notes here. Okay. So I think we'll take another problem with analysis. We'll solve exactly what is given, and later we'll go for the study of inverted and compound manometer. Okay. So that I will just explain. You can just follow the procedure and the concept should be clear. Okay, one more problem will solve to understand the procedure. So this is also differential. This one you can see. Yes, this one you write down. This is different type. A manometer connected between two pipes as shown. Okay, so these are the two pipes PA and PB. Both are at different levels. Both are connected by this U tube. See the small tube. It is having two U shapes. One on left side, one on right side. Two U shapes are there. So where the mercury liquid is there, here mercury is shown here, Hg. Take density of water 1000 kg per meter cube. No need to mention actually. at present, because we all know that standard value of density of water, density of mercury, we know it. Then see, in spite of giving 13,600, they have given 13,590. The quality of the mercury may be different. Pressure at A is 400 kilopascal. G is also they have given. So it is very uh, easy for everyone. So you need not to remember all these constants. G is 9.81 meter per second square. Find PB. So here PA is given. I think all the heads are also given clearly. Then one can find out the unknown value of PB. So find PB in kilopascal. This value is very important. Kilopascal, the answer should be in this unit. So now we'll see this problem. So both side water they have mentioned. Okay. So water, we know the properties. Mercury, it is filled in one of the U2. This also we know the properties. Then heads, if you see here, what are the heads given? The level of mercury and center of the pipe, if you see the distance or the water head, what is generated here, the vertical head is 2.5 meters. We are not bothered about the curved nature of the pipe here. We are bothered about the vertical head, because hydrostatic law bother only about the vertical heads. Then at this level, lower side of the mercury, what you have taken the datum line, from this we are going to measure the other heads. Mercury level from this datum to the interface of the water and mercury, that is 1 dash to 2 dash datum, if you consider, that level is up to 0.6 meters. So water head on the left side is 2.5 meters, mercury head is 0.6 meters. Again, see here, as I told you, once you draw these datum lines, 2 2 dash or 1 1 dash, the head due to this curve or U2, we are going to neglect it. Both sides same head. So even though if you consider the problem, it will be neglected. So we will reduce the terms in the problem. Then remaining is 2 dash to pipe center B. So in this part, the pressure head developed or the head developed by this water at pipe B is 0.4 meters. So all the values are given in meters. Now we have to go by procedure. How to write the equation for this given manometer. So here either you can take PA and head of PA with 2.5 meters head separately, and you can make it equal to other sides of the PB. Or else you can take the separating line at PB pipe. Okay, you can take the head of the pressure of the PB and head of the water head on the right side, and you can equate to other side. But here important is which side is having maximum pressure. The PA is having maximum pressure. So from that side, if you start, okay, what we can write now? Again, going to the downside, we can add. So PA plus rho G W. See, rho G of water on the left side. On the right side, if you see here on the right side from the datum line, it is low W or water on the right side equal to PB plus this head from 1 to 2 dash. The mercury head is rising. Is that clear? Or what you can do? We can take mercury head as rising on PB side, because of which the liquid or the water on the PB side will be lowering downside. Is that clear? So this equation also you can take on other side. Rho G H of water on right side, you can take it with minus sign. You can write PB plus rho G H of mercury minus rho G H of water on the right side. Because we need to write equation such that we are going to take that partition line here between pipe PA and the mercury level. Say for example, here I will take the partition line. On the 0.6 meter line, I will take one partition. I will write only these two equations, PA plus rho G H of water on the left side over equal to, as per our procedure, mercury head is rising here. Earlier case, it was kept open to atmosphere and it was rising upward. But here what is happening? Towards PB, the water level is trying to push the water towards PB because PA is more. Okay, this is in the differential manometer, and the liquid water, if you see, as per the mercury head rising, it is starting to pressurize towards PB. So that term will become PB plus rho GH of mercury rising. Lowering is what? Water level or the liquid level in the PB will be lowering. That is minus rho GH WR right side. On the other side you can write. Any confusion here? If all of you understand the writing equation or balancing the heads of manometers, you can solve any type of problems. No doubts? Yeah, rising in head is taken as positive or negative. So as per our normal YouTube manometer, we are taking lowering or the pressure from which pipe it is coming outside and lowering. We are taking it as positive on the left side for the left side pipe. Okay, see here. Yes, in this example, the pressure on A is more. So pressure of the water is trying to push the mercury downside. So with respect to pressure A or pipe A, this 2.5 meter head, whatever is there on the left side, we are taking it as positive. It is trying to push the mercury level. So means it is with the water level and it's trying to push the mercury level on the below side. So both we can add. This is the total pressure what is acting on the mercury, correct? And as I told you, other pipe with the remaining U-tube I have considered on the right side. In that case, if you see, starting from the left side only, so here in the mercury level, if you see, mercury level is rising on the right side. It is rising by 0.6 meters. So this is a positive pressure, or this is the pressure due to pipe A. This pressure is trying to push the liquid of pipe B towards pipe B only, which is moving downside. But with respect to PB, if you see, if the PB is having positive pressure means it should rise this liquid upside and try to push the mercury level downside if it is having more than PA. But here what is happening? The pressure is more towards PA. That's why the mercury head is trying to rise upside. Okay. So upside it is rising and it is lowering the water on the other side. So what I can write here? PB minus of rho GH of water on right side minus mercury, or I can write it as PB plus of this mercury. Both are the pressure present, but here what is opposing it? The water which is coming towards the pipe B, that itself is opposing the rise of the PB liquid or liquid present in the pipe B. So as per their line of consideration of equations, they have taken this line, I think, at above U2. So from that they have considered, they have taken all the positive signs here. Because mercury is also rising means it is supporting this PA pressure. Because of the more PA pressure, mercury level is rising on other side. So it is helping this PA pressure A. So that's why they might have written this also, or you can write PB plus rho GH of mercury minus of this. Any one of the way. Okay, you solve this problem. We'll take another two examples. I'll explain the procedure. I'll explain only the procedure. Later you can solve the problems. Yes, any replies? Okay. So check these values. 400 meter. Water on the left side. No, no, pressure. Sorry. PA is given 400 kilopascal. Yeah. 400 kilopascal will keep as it is because PB will be in kilopascal. So don't convert it. 400 only because we need answer as kilopascal. Then rho g h of water on left side. So 2.5 meter is given here. Rho g h you can write down plus this water level on the right side, rho g h equal to PB plus mercury head. So mercury head again, if you observe, as we have taken positive signs for the lowering liquid heads with respect to pipe A, this is rising liquid head. So on left side only if you consider, I can write PA plus this liquid head lowering, then minus of this mercury head which is rising. But on the PB side, if so here we all need to practice so that we can understand the procedure. So take the density of mercury what given in the problem, because we cannot assume here standard 13,600. In the problem they have little bit changed the values, 13,590. Check the answer. PB is lower than PA as per sketch. Yes, PA is 400. PB should be less than 400. That is one general conclusion. But how much it is less, we need to find out. And now, can anyone tell me from this example whether this PB is gauge pressure or absolute pressure? What PB we have found out or PA is given, whether it is gauge pressure or the absolute pressure. Is any replies? Yes, very good. This is the gauge pressure because here the pipe is not kept open to atmosphere or anywhere there is no atmospheric pressure acting. If atmospheric pressure is acting in any side of the pipes, then we would have added that atmospheric pressure. That will become absolute pressure. Is that clear? So as those all pipes and YouTube all are connected each other with respect to inside pressures without exposed to atmospheric pressure, that's why we are calling it as gauge pressure. So any time if you connect a gauge here and find out what is the pressure at pipe A and pipe B, that is the device pressure only. That is 348.5108 kilopascal at pipe B, and pipe A is 400 kilopascal. Okay, later you can check the values. All of you completed this problem? Okay. So next we'll take one compound manometer and inverted manometer. Similar type. We'll understand. Just will understand. Later you can take down, or else I can share the PPT also. So just will observe how to write the equation for those type of manometers by using same principle. Okay. Yes. Screen is visible to all. This compound manometer is visible to all. Okay. So in this example, if you see, just I'll read the given data and we'll check how they have written or what is our procedure. As per our procedure, whether it is correct or not. Okay, we'll check it. So in the figure 2.36 is shown a compound manometer. Compound means number of U-tubes will be there. Differential U-tubes. There are number 1, 2, 3 like this. And one of the example also we have solved. And this manometer is connected to both the pipes, not to the atmosphere. So here also they are measuring the gauge pressures. Calculate pressure difference between the points A and B. Okay. Take water. So water side pressure is 10 kilonewton per meter cube. Okay. For water. Sorry, what is given there? WW. So I think it is rho g value is given. Specific weight is given. Specific weight is 10 kilonewton per meter cube for water. For mercury, specific weight is 136 kilonewton per meter cube. Yes. So specific weight, small w, we have discussed in earlier cases. Water, 10 kilonewton per meter cube. Mercury, they have given 136 kilonewton per meter cube. And oil, for oil, specific weight 8.5 kilonewton per meter cube for oil. So these values are given, rho g values are given, and H are shown in the sketch. So here, wherever the red color is shown, the red color liquid, that is the mercury. And in between these mercury levels, the oil is kept here. So two liquids are used in the U-tubes. One is oil, one is mercury. And at the pipes, it is water. Both the pipes, water is flowing. So water is flowing at different pressures. And they are measuring, trying to measure with the compound manometer here. This is the manometer given. So now we'll see all the heads. So head due to this water in the pipe A is 1.08 meters. So with respect to pipe A, it is acting downside, means it is trying to push the mercury downside. So it is PA plus this value. I hope this is clear. Now coming to our same procedure, as the pressure is acting downside with respect to gravity, it is supporting this PA only. So we are adding PA plus this value. Now other side, if you see, it is rising, mercury head is rising. That what we discussed, we can add it on the other side, or we can take it subtraction on the same side, because it is rising, this is lowering. So lowering with respect to the same pipe in the normal U-tube manometer, it is positive. Mercury head is rising, we can take it negative. So that's why they might have written this WM 0.72 like that. And oil, if you see, oil on the other than this U-tube section, I'll not consider the U-tube section heads, both are same. 0.48 meter head if I take, it will be lowering. So with respect to PA, oil head in between the manometer, it is trying to push the mercury downside again. So that is also supporting. If it is lowering, it is supporting. So that what we are writing as per the sign convention plus pressure head of the oil. Then again on the right side, if you see, mercury head is rising. So both these mercury heads are rising on the right side. With respect to pipe A, it will become minus. Minus of mercury pressure head, minus of water. Now can you tell me, for water, how they considered it is negative. Why not positive? Yes, because here what is happening? As the pressure of pipe A is increasing, by the sketch, if you see, by the sketch, we can also come to the sign conventions. By the sketch, the pressure A is more, means what will happen? Earlier, the pressure in the pipe B side may be lower side, but once the pressure is becomes high on the PA side, it may trying to push. So once it try to push, because of the mercury head, we understand that this level of liquid is acting towards PB. Are you understanding? So if it is acting towards PB, then I can take it negative equal to PB, or what I can do with respect to PA, it will become opposing pressure. I will take minus PB equal to 0. So in one whole equation, we can write it all the terms plus minus and other things. We can equate to 0. This is also one of the procedure. Okay. Or else what we can do? We can take one of the section here. At 0.72, I will make a partition. I'll take PA plus this level of water on one side. Other side, I'll try to balance. What is that? Mercury head positive. Okay. Mercury head in positive minus oil level, because this is rising, we have considered positive on the right side. This will become negative. Again, this will become positive on the after partition of the U2. Then this PB value is supporting this liquid as per the other side of the liquid, that will become PB plus this value. So either you can write partitioning or dividing the U2 into number of parts, or you can write one whole big equation with respect to P and PB as given in the sketches. Any one of the form you can write. So I hope by this example, at least many have understood the procedure of writing the equations. Yes. It's rising with respect to PA. Yes, correct. Yeah, mercury heads are rising with respect to PA. Okay. One more last problem will take self-study. Just will understand the procedure what they have followed. So this is example of a inverted manometer. Inverted U2 manometer. So only thing here, sign convention will change. So again, they have given an inverted differential manometer is connected to two pipes. Shall we continue the class? Or you need a break? Okay, better we'll take a break. We'll come back at 11. Okay. We'll continue. Am I audible? Okay, screen is visible to you. This screen. Okay. So this will understand by taking the last example. So here inverted manometer is connected with two pipes A and B as shown in the sketch, carrying water under pressure at as shown in the figure. So again both pipes are with water. The fluid in the manometer is oil of specific gravity 0.75. So in this example they have not taken mercury as a liquid, they have taken other high density liquid like oil to measure the manometer difference. Determine the pressure difference between A and B. So in this problem they are not asking to find what is the actual value of PA or PB, they are asking difference. And if you see the manometer, it is completely inverted opposite to the other cases, earlier cases. And here maintaining the oil head in the manometer is very difficult because whenever there is no flow in the pipe A or pipe B, the manometric liquid may come out. So always we need to maintain some pressure difference or some equal pressure at least, so that the oil in the inverted manometer can be maintained in the manometer or the device. So this is one of the difficulty. So many times because of the space concern or something, they may go for inverted manometers. So but regularly if you see many times U2 manometers or differential manometers, downside is used, not the inverted type or the upside. Okay, now we are bothered about how to write these equations so that we can find out pressures or the head. Okay. Now coming to this example, now from the sketch one can understand pressure A is more than pressure B. Yes or no? Because the water in the pipe A is trying to push upwards the oil which is present in the manometer. That oil is pushed upwards because of the more pressure from pipe A. And pipe B, if you see, comparatively as per sketch, it is lower pressure because oil head as well as the water head on the right side, both are trying to push towards PB. I hope all are understanding. The manometric liquid oil and the water head on the right side, if you see, both are trying to move towards pipe B because of the more pressure on left side. And coming to the equations, I can write like this: PA minus of, because this pressure from the pipe water is coming out in the inverted manometer, it has to move upside. So just keep in mind that it is overcoming the gravitational force, or it has to overcome the pressure of pipe B, or it has to overcome the pressure of oil. Okay, so I can write it as PA minus upward direction of the liquid column as per our convention will go. If it is downward direction, if the pipe pressure is A is more, it is supporting the pressure. But here if you see the pressure column or the column of the water which is upward side, as per our sign convention we are taking PA minus. And in the example given also, in the sketch also you can analyze like this. The pressure on the PA is more, that's why the liquid column is coming outside and trying to push the mercury column in the upside direction, not the downside direction. So I can write it as PA minus, what is the head of the water here on the left side? It is 450 mm. So 450 mm I can take with water, rho g h, rho g of the water we know, h is 450. I can write. I can make the partition here in between, equal to I can write, other side, right side. Right side if you see, the mercury column is trying to push the liquid of pipe B towards pipe B only in the inverted manometer. Means it is trying to reduce or overcome the pressure of pipe B. So what I can write? I can write PB minus of rho GH of mercury. Rho GH of mercury, H is not given here. Now what I can do, I can find out by difference. Okay, so on one side with the same pipe B level, they have given both the dimensions. So I can take left side dimension total 450 plus 200. Okay, that is how much? 650. 650 minus 450. So that difference I can take it as X here. That is the oil head, not mercury. Oil head I can take. So this rho GH plus this rho GH of liquid column, both are acting towards PB. So PB minus these two columns. I can write it on the right side. Did you understand, all of you? You can add both the columns on right side. Take a negative sign for the PB side, or you can take PB minus of water column on the right side and the mercury minus oil column on the right side. That also can be done. But in the inverted manometers, the rising and falling is opposite. So that's why sign convention will change here. And this you can compare with our examples, what we considered in the notes here. This type you can check. Here what we did, PA, see here, because of the high pressure in the PA, it is easily moving downside because of the gravitational force. Like that you can think. Otherwise, other than lowering or rising. Here it is lowering side. So I can consider PA plus this column equal to, I'll take the partition line, equal to, see here, equal to, there is no mercury column, but there is a mercury column on the left side only. So left side only means what I can do, as it is in the lower side of this same column, okay, I can take it as positive because it is towards PA. Then I can equate it to PB plus this liquid column on the lower sides. Or you can start from PB only. So considering PB as a high pressure because mercury level is rising towards PA, what I can do, PA plus rho GH on the right side, this liquid column. Okay, PB plus this liquid column I can write equal to, see here, mercury column plus liquid column plus PA. All are towards PA in this type of manometer, which is normal type. So PB side, wherever it is high pressure, you can start from that end so that convenience will be more here. So PB side pressure is more, so that we'll add the lowering side pressure. On the left side, the pressures are rising. So liquid columns are rising here. What they are doing, rho GH of mercury, rho GH of liquid on the A side, they are rising towards A. So here we are adding earlier. So similar case in the inverted tube, it will be opposite. So here on the pipe A, pressure is more as per this. This is trying to push upwards. So when liquid moves above or it will rise with respect to PA, we are considering PA minus this liquid head. On the other side, what we are doing, PB, these liquid columns again are towards the PB. We are taking minus of these two heads. Or can take PB minus of water head minus of oil head. Is that clear? So always take the high pressure side to start with the equation. So which are the column of liquid is trying to push the liquid downside, you can take positive. If it is upside in the inverted manometer, you can take the negative sign. Yeah, with respect to A only you can take. That is also possible, but one should keep in mind whether the left side pressure itself is more or low, because in this example what I considered, this is opposite. Here if you see, this is opposite. PA side is low pressure because mercury manometer is coming upwards. So you can start with the high pressure side PB also. One understand. PB side means our same procedure. High pressure liquid is pushing the mercury downside. So PB plus this pressure I can add. Other side I'll add these all pressures in the regular manometers. But in the inverted manometers it is opposite. Okay, shall we move to the next part? So from the notes I have solved a different variety of the problems on manometers and pressure measurement. You can refer the notes, and anything is missing what we have not discussed in this class, then just refer these remaining problems similar type, so that you can practice and understand the equation, how to write the equations and other procedures. Okay, some problems are not solved, so this you can all take the examples and you can solve it by referring the examples. Okay, now we'll come to the other part, that is finding the hydrostatic force on the surfaces. So before going to this topic, one should understand where these hydrostatic forces are going to act. So all of you know what is hydrostatic law. That is, whenever the liquid columns are present and whenever the fluid is not flowing or it is not acting by the external pressures and other things in the fluid statics, there, as the level of water or the uh, points of the water, if you consider from surface to the bottom, the pressure goes on increasing as you go downside. Okay, so this is earlier we defined by the hydrostatic law by taking P equal to rho g z. So rho g is the liquid properties, density and the gravitational force. Z is what? The depth of the liquid. So as you move according to the depth, the pressure of the liquid or the forces on the liquid particles will be increasing. So pressure is the force acting per unit area. On the area, if you consider complete force acting on the given area, that is called as pressure. If you consider a point where a simple force is acting, that we are calling it as a force. So force will be acting always on the point. Okay. Or if it is acting per unit area, for a given area, then we call it as pressure. So here we need to find out how the pressure or the force distribution will be taking place along the depth of a surface. So example, if you take, we have the examples of the gate, dam gate or the wall of the gate. So here I have taken examples. So first example, the top sketch, if you see, so don't bother about the dimensions there. If you check the dam wall, so on the wall, if you see, it is slope, it is made up of like a slope, and it is a, I can consider it as an inclined surface. On this inclined surface, the water is filled on the one side, other side it is kept open to the atmosphere. So what will happen from the water surface? So here this inverted triangle shape you can see, that is the water surface. That is indication of surface of water which is kept open to atmosphere. From that surface, if you take the surface of water at the tip of the dam near here, where the intersection is there, there the force applied by water will be very less because it is at the surface. Rho g z value if you take, z will be 0. So exactly surface line if you consider without any difference of head, then the pressure may be negligible, 0. But as I move downside, what will happen? The rho g z value, the z value or the h value is goes on increasing as we increase the depth. Okay, so due to this weight of liquid or the density change of the liquid with respect to head, because of this what will happen? The pressure value goes on increasing as you go on moving from the this tip to the lower side of the wall in the inclined surface. If you go down, the pressure at this downside point will be very high. Okay, or if I go below 700 feet, it will be maximum. If I go in between, it will be half. So like that, pressure or the forces on this surface of the dam is going to change from lower to higher as you go on with the depth. Similarly, one more case I have taken. a gate is fixed here below the water container, and water is assumed again in a static condition without any flow, without any external forces. So only by gravitational force how the water is stored in the container and how it is going to increase the pressure head or the forces as the we go the bottom side. Now this, if you see, just for operating the gate or the surface, the vertical surface, they have fixed one hinge there. So about that hinge it is going to rotate just to open and close the opening of the water flow. So once it is closed, I can assume the water in static condition. Then we can take the pressure acting on this wall. So pressure acting on the wall or the canal, if you see above surface, the dam or the wall surface, it is going to increase from tip to the bottom surface. And whenever the hinge opens this wall, what will happen? The water flow starts. So in such cases, we cannot consider this hydrostatic law or the hydrostatic forces. So hydrostatic forces can be considered only when the liquid or the water is in stagnant condition or in a static condition. And this type of surfaces, if you see, it may be circular wall or it may be a triangular shape. So here all we are taking standard shapes, but actually seeing in the real examples, the shapes of the given wall of the dam and other surfaces like canal surfaces or the channel of a gutter, if you see, the surface may be uneven. But here in the syllabus, we are considering all standard shapes where the pressure is acting on that surfaces. So above, if you see, it is an inclined surface. Below, if you see, it is a vertical surface. And here one more example I have taken, how the gate of dam is opened. So by different mechanisms or different shapes, they are going to design the gate of the dams. So whenever the water is overfilling or it is crossing the limits, then what they will do, they will lift this gate. So this gate is, before opening, it is acted by the forces due to water which is stored in the dam. And even this bottom side dam wall, if you see, that is also acting with the pressure forces. But here in the syllabus we are considering on these surfaces, either that may be inclined, vertical or horizontal. In such surfaces, how these pressure forces are going to act, how it is going to change with respect to depth. Okay. So I think all of you understood how these hydrostatic forces are acting on the different surfaces. Shall we move further? So here we are considering one surface which is supporting the liquid in a container. So in such cases, we are considering the forces acting on that surface are, one is fluid pressure normal to the surface, that is nothing but perpendicular direction. If the surface is vertical, water force is acting in the perpendicular direction to that. One more is self weight of the fluid due to gravity. So this self weight will be acting on these examples, not on vertical. Here if you see, the weight of the water is acting at the downside here. Okay, not on the wall. But here in the vertical surfaces, we are considering only normal pressures or the normal force which is acting on the vertical wall. But here if you take inclined surface, the dam surface, here what will happen? The weight of this liquid part is also acting on the surface for the inclined surfaces. Or whenever you see the inclined gates also, in such cases, the weight of the liquid as well as the pressure force, both will be acting. The four cases of submerged surfaces with total and center of pressure, we are going to consider in the syllabus: vertical plane or the vertical gate. You can take example, horizontal surface, and inclined planes. So curved surfaces we are not discussing, but we will see at the last if any examples can be taken. So keeping in mind for the vertical surface, the hydrostatic law will be coming into picture because of the depth. But for the horizontal surfaces, only weight of the liquid is going to act. The depth of the liquid, whatever the hydrostatic force is going to act, that is not going to coming into picture for the horizontal planes. And for the inclined planes, as we told here, weight of the liquid as well as pressure which is acting perpendicular due to hydrostatic force, both forces are going to act on the inclined plane. So if you try to understand this inclined plane on which how the forces are acting on the inclined plane, this will cover the concept of horizontal plane as well as vertical plane just by changing the angles. So we'll take inclined plane as an reference and we'll try to understand how the forces are going to act on the inclined plane. Then we'll change the angle with respect to horizontal or vertical. Then we'll understand how the forces are acting on the vertical plane or on the horizontal plane. So we'll consider one inclined surface here. Okay. So inclined plane surface submerged in the liquid. So I'll assume this surface AB. So A and B, whatever is written in red color, is the surface. A thin surface is kept inclined in the submerged liquid. So assume water, it is kept in the water, and above which the water is completely filled here. And on this inclined surface, which forces will be acting? One is weight of the liquid and the forces due to hydrostatic pressure, that is P equal to rho gh. So as you go on increasing the depth, the forces acting near to B is more and forces acting on A will be less. So just draw this sketch taking AB plate. This is the side view. AB is the side view. Top view I have shown with the irregular surface. We'll assume some irregular surface. Means I have taken any plate on which I will consider center of gravity of that plate, point G, center of gravity. And we'll assume center of pressure may be this side. Why? Because as I told you, from the initial point A, as you go on increasing the depth, the pressure forces will increase. Rho g h value will increase because of the increasing head values. This h bar, h star, if you see, the head value is increasing of the water. That's why the pressure at the bottom side will be more. If I consider complete surface and the center of pressure, I'll assume this P as the center of the pressure for a given plane. Complete plane, if I consider this, I will take the pressure point. So first draw the inclined plane AB. Draw a top view just for analysis. Top view you draw. Show one center of gravity point, then center of the pressure point. So next with this, we'll consider some angle between this inclined plane and the free surface of water, that is theta. And for a given surface of or this plate, we'll consider a small area. So we all know that we consider small area and small forces, then we'll integrate for the total forces and total area. So for that case, we are taking a small area here on the surface of the plate on which the pressure is acting or the force is acting. That small area we are taking dA at a distance of y from the tip of the plate A. So from the tip of A, you just draw a line here, perpendicular line at A and B to draw the top view. And from the top side line OO line, you can draw one line. So at distance y, any distance, you can take at top side or bottom side, you take one small area dA. And the distance between these two lines, between the dA, I can take it as dy. dA and dy. dy is the distance. dA is the total area on which the force dF is going to act for the reference. Next is, for this area, we have considered the head of water acting on this area is h, small h, at a distance of y. So similarly here, whatever the y distances you have taken, perpendicularly you have to take for the water surface, I will call it as h, head or the z. So head h I have considered for the small area. And for center of gravity point, we have considered y bar. From the plate tip, if you see, at a distance of y bar, we have considered g, and vertical distance from this plate in the side view, if you see, the vertical distance from the water surface to the inclined plate section, if you see, that distance I am calling it as h bar for the center of gravity of the given plate. Is that clear? And for center of pressure, I have taken the distance. So center of pressure is acting at a distance of y star from the tip of the surface, or h star from the free surface of water to the pressure point P on the side view. So all the side view dimensions I have written with h, h bar, h star for small area dA, h bar for gravitational, center of gravity, h star for center of pressure. Similarly, for the top view, in the top view, from the tip of the surface O, I have taken y for dA, distance y bar for center of gravity, distance y star for center of pressure. So these all details are given in the below. What is h star, what is h bar, all these things. So once you complete this sketch, just inform me. So take the sketch so that with respect to sketch, if you analyze the given derivation, one can understand what is the importance of this hydrostatic force in submerged surfaces. All of you taken the sketch? Okay. So please understand, in the sketch we have taken a plate, inclined plate, you can assume any shape, and on that plane we need to find out what is the forces acting, total forces, and center of that point, or the center of that pressure point. So for that, what we have done, we have taken a plane, we have taken a small area there. Before going to the total forces, we have taken small force dF, small area dA, and we have taken some distances so that we can write some relation between the given values. And between that inclined plane and surface of water, if you see the inclination, that I have considered theta here. You can recall this sketch. Theta we have taken. Now we know that inclined dimensions we know in terms of y, and vertical dimensions we know in terms of h. So by which relation we can connect this h, y, and theta? Can you tell me? Opposite sides are known, these hypotenuse sides are known, but we don't know adjacent distances. What we can consider? We can consider sine. Yes, yes. Sine is opposite by hypotenuse. So we can relate h and y values, and later we can take the forces also. Yes, after all these details, now we'll see what all details can be written. Now pressure intensity on the strip. So pressure intensity at given h value, because we have considered a small area at distance h here. See here, at distance h, small area dA we have considered, and that is acting with some small force dF. So that's why what they are telling, the pressure acting at that point, we can write it as rho gh, which is a vertical hydrostatic force. And similarly, I can write it as P as force per unit area. That is force by area, I can write P. So for a given small area, I can write it as dF equal to, I'll multiply this pressure into area. What is that pressure? Rho gh into area of the strip. That is dF equal to rho gh into dA. What we have done? Again, we have started with the hydrostatic law only. Hydrostatic law is different. Hydrostatic forces on the submerged surface is different. So from the hydrostatic law, we know that at any given point or at any given head, the pressure is rho gh. Pressure is force by unit area. So that force we have considered small force and small area for that strip of area. If you see in the derivation, for this strip, small strip, I can write it as dF equal to rho gh into dA, because we need forces here. So pressure I have converted into force. So now if you want to find out the total pressure or the total force throughout the area for complete area, as I told you, we'll integrate. So once you go for integration, I can write it as F equal to integration of dF equal to integration of rho gh into dA. So as far as integration is concerned, we are going to integrate only this dA, not this rho gh. Or h is changing, we can integrate only h into dA, not with the rho g. Rho g are the constants. Then as I told you, h and y, we need to replace some terms here. Or if you want to write h in terms of other ways, because h is denoting only the vertical level. But as for the plate, if you see, we know the distances as y. For the plate, on the surface of the plate, if you move, the y is changing. But on the surface of water, if you go on changing the values, the h is changing. So I want to replace this h with respect to y, because plate is not vertical here. If I consider h, we assume plate is vertical, but plate here it is inclined. Means in inclined direction, if I move here, what will change? Y will change, not h. But h and y are changing with respect to theta. So I will relate this h in terms of y. How? I will take sine theta equal to opposite by hypotenuse. So all the terms I have written here, h by y you can write, h bar by y bar ratio is also same, h star by y star also same, because you can see the ratio here. Theta is remaining same for given same theta value. H by y is same, h by y sin theta, h bar by y bar is also same, h star by y star. All the ratios will be same. That's why angle will be constant. So what we can write? I can write h as h equal to y sin theta. I can write h bar equal to y bar sin theta, or I can also write h star equal to y star sin theta. I hope you are understanding. So I will, after integrating force, I will write complete force acting on the surface. For complete area of the given surface, still we have not integrated. I will keep the sign as it is on the right side. Rho g. So wherever h was there, see here, above one equation, rho g h was there. I will replace with y sin theta, because we are talking about the surface, not with the water. With respect to water, if you talk, the height h we have to take. With respect to surface, if you are talking, you have to take y, inclined surface length. So y sin theta will take into the small area dA. So out of this, rho g sin theta are constant, y is changing, dA is changing, so we will integrate with the y dA. Okay, so write down up to here. Now once you integrate or consider for total area, I can write it as A into y bar. See here, A into y bar. So total area of the plate is A, and the point at which y is integrated from small y here, or dy, from dy to this, or small y to total y, I can consider it as y bar, because that pressure force is acting at the center of this center of gravity. So this becomes moment of inertia, first moment of inertia, or first moment of area. So one can write dA as A into y bar, where the forces are concentrated on the center of gravity. So now it will become total force acting on total area is F equal to rho g sin theta y bar into A. Or if you want to write it in terms of h, again replace this y bar. What we can do, sin theta y bar, here sin theta into y bar is equal to h bar, the above equation. In the first equation, I can write sin theta into y bar as h bar. So in terms of h bar, if you want to write, I can write it as F equal to rho g ah bar. You can write both the equations for total force acting for a given surface. You can write either with the inclined length F equal to rho g sin theta y bar A. With respect to vertical height, I can write it as F equal to rho g ah bar. Means the total force will be acting at the center of gravity. All of you taken the equations? Okay, total force and force point we understood. At h bar, the total force of the concentration of force is present. So the meaning of this equation is the total force acting on the total area of this plate is about this G point. That's why we are writing the equation with respect to y bar or h bar. Okay, either you can write y bar sine theta into rho g, or I can write h bar into rho g for that given area. Now we'll talk about the pressure. Now we'll find out what is the total pressure acting at the center of the pressure. So pressure is, you can consider it as moment of force. So force is moment of area, pressure is moment of force. So what we can do here, we assume that whenever there is a pressure acting on the surface or the force is acting on the surface, it is going to create some moment. So as per this plate, if I consider about A, there is going to create some moment so that this weight of the liquid and the pressure force of the liquid is trying to move this B to make it vertical. Are you understanding? So due to this, what we can do, we can take the moments also. Or even if I take the moment about this point A, what I can write? I can write F into or df into y. Again, df if I consider, I have to integrate. df into y, about that we are taking for small area, means here we are taking in the sketch the small strip, from the small strip to O is small y, here y into df. If I take, that is the moment of force. The moment of force, why you are taking, to consider the pressures. df into y, again take the same equation, rho g y sin theta. So y sin theta, or you can write h, rho g h into dA into y. So both sides I have multiplied with y to make it moment about point O or point A. Now again, taking the sum of moments of all such forces about O, if I take, what will happen here? Only we are going to multiply y into 2 times. So rho g y square sin theta. And if you go back to the geometry or the concepts of geometry, we know that area multiplied with some distance square is nothing but the moment of inertia of the surface. Yes, the moment of inertia of the surface is the area into distance square at what the moment is going to act. So I can replace this y square dA term in this derivation with respect to moment of inertia I naught. Or it is also nothing but the second moment of area is the moment of inertia. So first case we took moment of area here. First moment of area we took. Secondly, we took moment of, or the moment about point O. So we took 2 times moment, and that I can call it as moment of inertia. So after replacing this y square dA into I naught, I can write it as rho g sin theta I naught. So I can write it as df into y equal to integration of rho g sin theta I naught. Sorry, integration of y square dA, they have written as moment of inertia or second moment of area. force into distance, moment of inertia. Here, distance square into area. Here, distance square into area. If you take moment of inertia, not force into distance. Force into distance is moment about that force, or moment with respect to that force. We are taking about point O, that is dF into y. That is not moment of inertia. Yes. Okay, next, coming to this moment of inertia analysis, you can recall the again your geometry. So F into y star. So why they are taking y star? Because as I told you in the sketch, we have assumed the total force is acting at the center of gravity. The total pressure is acting at this point. So like that, if I consider, we can consider at y star for the complete area. So this F into or dF into y, what was there earlier, for total area we have considered the pressure force. That what you can write? I can write it as F into y star at the pressure center. F into y star equal to rho g sin theta I naught. And from the equation number 1, what I can do? Y star I can replace with what? Y star into sin theta is h star. So this y star into sin theta I can replace with h star. So substitute this y star and value of F, what we found out earlier. Because finally we want to find out this h star value. So vertically at which point the pressure center is located on the inclined surface, or the maximum pressure point is at the bottom, minimum pressure is at the top, and center of these all pressures, all these pressure points, the center is the pressure point what you have considered in the h star and y star distance. So in the numericals we'll find out what exactly that locations. Now once you replace these terms, so I can write F as rho g h bar from the forces, this one, F equal to rho g a h bar. So that is replaced here, rho g a h bar. Y star is replaced with h star by sin theta. And also we know that moment of inertia from the parallel axis theorem can be written as Ig, which is the moment of inertia about the center of gravity plus area of the given plate into distance square. So this is the center of gravity point. At center of gravity point, if you consider, I can write it as sum of Ig plus product of area into distance square at that point. I can recall this concept here. Parallel axis theorem. The moment of inertia I naught of any figure or the plane about an axis parallel to the centroidal axis is taken as. So axis parallel to centroidal axis. Here, which axis? Axis about G. If I take parallel to the axis OO. From this, if I measure the moment of inertia I naught, what we can do? It is sum of, or it can be written as sum of moment of inertia about the centroidal axis G and product of area and distance square between the two axes, that is OO and this G. Both these axes are parallel. So from the parallel axis I can write the moment about which it is acting is, we considered A point, the tip of the surface A. This is the tip of surface A. From this the moment is acting, so that's why we have written Ig plus AY bar square. So I think we'll stop the class at this moment. Next class will proceed with this moment of force, and we'll find out the point or the distance at which the pressure is located or the center of pressure is located. Okay. Yes. Okay. Thank you. Akhtar has given some more equations for 3D sketch, 2D sketch, and 1D. Very good. Okay, I'll stop here.